Good afternoon. My name is Robert Kacinski, and today I'll be discussing establishing a baseline computational model for examining benefits of high-flow nasal cannula oxygen therapy. Some quick background. High-flow nasal cannula, or HFNC oxygen therapy, is a non-invasive respiratory therapy in which heated and humidified oxygen is delivered to patients via a nasal cannula. High-velocity nasal insufflation is a subset of HFNC oxygen therapy in which the flow is delivered at higher velocities. The higher velocities are attained by a smaller inner diameter cannula prong, as can be seen by the cannula geometries on the right. Previous research concerning computational modeling of the human upper airway during oxygen therapy has had deficiencies in one or more of the following areas. The human airway is not anatomically correct. The breathing conditions are not representative of a real patient. For example, a steady case was simulated at one point in the breath curve as opposed to a transient simulation of the entire breath curve. Or, most commonly and most importantly, there is a poor or non-existent validation discussion. This is critical in any computational modeling, as if there's no validation discussion or establishment of numerical independence, which will be covered more later, then there's no way to trust the results garnered from the model. This study aims to create a novel CFD model that can be used for future studies examining non-invasive respiratory therapies that fixes all of these prior issues. The validation methodology used during this study was to collect experimental oxygen information using a 3D printed airway geometry that exactly matched the 3D geometry used to generate our meshes. An ASL 5000 was used to collect oxygen information during the experimental study. Numerical independence was then established through the use of time step and mesh independence. 4 time steps were tested to ensure the time step was small enough to be used for transient studies without losing too much information in between time steps. 3 meshes were generated at increasing cell counts to be used for the mesh independent study. Oxygen information was collected for all models and at the end was compared to the experimental model and conclusions were drawn. The meshing process began by collecting CT scans from numerous patient demographics. The CT scans were then imported into Slicer and 3D geometry files were created. These 3D geometry files, along with the cannula geometry file, were imported into SpaceClaim. The cannula was aligned, as can be seen in the figure on the right, and the fluid domain was modified to be suitable for meshing. The SpaceClaim document was then imported into Fluent Meshing, and an unstructured polyhedral meshing workflow was followed. This mesh was then imported into the Fluent solver, and final cleanup steps were done. After the meshing process was complete, boundary conditions were prescribed. At the airway inlet, a user-defined function was used to control the volume flow rate and species concentrations. The volume flow rate followed a realistic patient breath curve that was also used on the ASL 5000 to collect experimental oxygen information. The species concentration was set using volume flow rate averages during inhalation that was then used to prescribe the species concentrations during exhalation. The cannula inlet was a steady input of 100% oxygen at 35 standard liters per minute. The environment outlet was a pressure outlet with species feedback of 0.21 mole fraction O2, which was used to describe ambient air in the room. Solver settings and turbulence models were broken down into 2 distinct groups, LOSST and HODRSM. LOSST included the highly popular, but inaccurate, K-omega SST turbulence model, and fluent default discretization schemes and transient formulations, making up the lower order solver settings. HODRSM included the differential Reynolds stress turbulence model, which is a linear eddy viscosity turbulence model, much like the K-omega SST, but it is more computationally expensive while being more accurate. Higher order solver settings were also investigated, which included higher numerical rigor and less numerical diffusion, while sacrificing computational cost in the process. Throughout the rest of the study, the metrics will be divided into 2 groups, coarse and fine. Coarse metrics are average metrics that are often used during validation studies due to them being easier to compare to experimental data. Fine metrics are highly unsteady metrics that are often ignored when establishing numerical independence and validation. That is because they are difficult to compare to experimental data. However, they are vital to properly establishing numerical independence. During the refinement studies, data is normalized by the mesh or time step 1 value. For the time step study, this means that all data is divided by the initial lowest time steps data. They are then plotted by percent of largest time step value or percent of smallest mesh refinement value. They are also broken down into fine and coarse metrics as can be seen by the plots on the right. For the fine metrics, the highly unsteady metrics only show a 7% statistical variation at its maximum, which is integral length scale, or ILS. Due to their highly unsteady nature, this is considered acceptable when establishing time step independence. For the coarse metrics, a 1% variation is considered significant, which is the variation between the 800 and 4,000 time steps per breath. From 4,000 to 8,000 time steps per breath, there is no change. Due to this, 4,000 time steps per breath was considered time step independent. Mesh refinement was broken down into LOSST and HODRSM mesh refinement studies. The fine-grained metrics showed very little variation compared to what was expected, especially the local turbulence metrics, TKE and ILS. The maximum variation from Mesh 1 to Mesh 3 was a 30% change in TKE. Mesh 3 was considered to be of acceptable refinement because the established trends showed that there would be no significant changes with further mesh refinement, and these changes would be outweighed by the increase in computational cost. The coarse measurement, mole fraction O2, has a counterintuitive trend with mesh refinement. The experimental value of O2 is 0.738, and as the mesh is refined, the O2 value at the airway inlet moves further from this point. For HODRSM, the changes in fine-grained metrics seen in the figure on the top are not significantly different than for LOSST. For the turbulence metrics shown on the bottom left, there is over an 8,000% increase in TKE compared to a 30% increase for LOSST. This is substantially different, and it can be used as evidence of lower numerical diffusion for HODRSM when compared to LOSST. For the coarse metrics shown on the bottom right, the O2 follows a trend that would be expected. As the mesh refinement increases between Mesh 1 and Mesh 2, there's a substantial increase in the accuracy of the oxygen at the airway inlet. Between Mesh 2 and Mesh 3, the change is considered statistically insignificant. However, due to the turbulence metrics changes, Mesh 3 is considered mesh independent, not Mesh 2. This is used for the final validated model. A summary of the oxygen results can be seen in the table on the right. For all models using HODRSM, when compared to LOSST with all modeling parameters being equal, the HODRSM showed improved oxygen accuracy when compared to the experimental value. The final validated model is shown in green, which is higher order solver settings, differential Reynolds stress turbulence model, Mesh 3, which is 8 million cells, and 4,000 time steps per breath. This resulted in an oxygen value only 0.4 percentage points away from the experimental value of 0.738. Notice that there are 3 models in between the final validated model and the experimental model in terms of accuracy. These models all are far from numerically independent, with all of them using Mesh 1, one of them using lower order SST settings, and that same one also using only 128 time steps per breath. This was the first model run in the study. This highlights the dangers of poor validation methodology. If only coarse metrics were used to validate the model and establish numerical independence, then a researcher could be led to believe that this initial model was actually numerically independent and ready to be used for further testing. The final validated model can now be used for further studies examining non-invasive respiratory therapy. Numerical independence was established, and the final O2 value was only 0.4 percentage points away from the experimental value, which falls within the 0.5 percentage point expected error of the sensor used to collect experimental oxygen information. The validation process must include establishment of numerical independence using fine-grained measurements. If only coarse measurements are used for the establishment of numerical independence, then the premature establishment can occur, which will lead to a model with conflating errors being accepted as validated and independent. The commonly used K-omega SST turbulence model, as expected, is highly diffusive when investigating local turbulence metrics.